Every glass tower on Earth is bleeding money. Buildings burn more energy every year than every car, plane on the planet combined, and billions of square meters of glass hand nothing back. To pull power out of sunlight, a material has to turn black and swallow the light whole. To work as a window, it has to let that same light straight through. For 20 years, nobody found a way to do both at once. Then, one breakthrough quietly turned an entire skyline of ordinary windows into a power plant. It took two research teams, working in two completely different ways, to make it happen. Solar panels are black for one blunt reason. Black means the material is swallowing every photon that hits it, turning light straight into electricity. A window doesn't get that luxury. The moment glass grabs enough sunlight to make real power, it quits being a window and turns into a tinted panel with a building attached to it. Labs in the United States and in Germany spent 2 decades chasing a version of glass that could do both at once. More than one of those programs lost its funding before a single usable panel ever left the building. One widely cited attempt landed at a conversion efficiency of 1.57%, next to rooftop panels already sitting at 20. That gap wasn't a technical footnote. It was the difference between powering a building and powering nothing at all. Cost made it worse. Early transparent solar glass ran 4 to 8 times higher than ordinary architectural glass, for a fraction of the electricity a cheaper rooftop panel already delivered. Architects looked at the numbers and picked something else. For 20 years, the idea just stayed on paper. Then 2 teams stopped trying to solve it the same way. One decided the glass needed to work harder. The other decided the glass shouldn't have to do the work at all. The first path came out of Nanjing. A university research team stopped trying to make the glass itself generate power and started asking a different question. What if the glass never touched the electricity at all? This team built something stranger. A coating just a few molecules thick, tuned to grab one very specific angle of sunlight and let everything else pass straight through untouched, like a scanner that only reads one exact barcode and ignores every other item on the belt. The sunlight that gets caught doesn't stop at the glass either. It bends sideways, travels through the pane the way light moves through a fiber optic cable, and comes out only at the very edge, where a thin strip of solar cells is waiting to catch it, hidden inside the window frame. In real testing, the coating let more than 60% of daylight pass straight through, close enough to a normal window that most people would never notice a difference. A prototype the size of a coin ran a small fan outdoors, powered entirely by light pulled in at the edge of the glass. Not everyone agreed that bending light to the edge was the answer. A different team picked the opposite fight. Instead of routing power away from the glass, they decided to break the efficiency limit right in the middle of it. Their glass doesn't redirect light. It eats it, the same way a rooftop panel does, using a paper-thin film built directly into the glass during manufacturing instead of bolted on afterward. One Chinese glass manufacturer, Mingyang, had already been mass-producing a version of this for years. A thin film of cadmium telluride, a light-absorbing material long used in solar cells, fused straight into the glass on the factory line. In late 2024, they stacked a second material on top, perovskite, a crystal structure currently breaking efficiency records across the entire solar industry, tuned to catch the light the first layer let slip through. 2 answers to the same 20-year wall. One team never let light touch the middle of the glass. The other team never stopped trying to make the middle of the glass do more of the work itself. Neither one is finished. Both are already sitting on real buildings, generating real electricity right now. None of this comes cheap yet. Transparent solar glass right now costs 2 to 3 times more than a standard architectural pane, and neither team has driven that price down to something a developer signs off on without hesitation. The Nanjing coating has only been tested at the scale of a coin and a 2-meter simulation. It has never gone up on a real office tower. Mingyang's tandem film has the head start there. It already runs on a production line, but that line is barely a year old, running a material nobody has watched survive 20 years of weather yet. Perovskite is a strange kind of powerhouse. It converts sunlight almost too well for how fragile it actually is. Too much heat, or a single drop of rainwater slipping through a crack in the seal, can start breaking the crystal down from the inside. Engineers now spend nearly as much effort keeping water and light away from it as they spent getting it to generate power in the first place. Then there's an enemy nobody expected: the building code itself. Most fire, safety, and electrical codes are decades old, and they were never written to answer one basic question: is a power generating window a piece of glass or a piece of electrical equipment? Until regulators pick an answer, both technologies stay stuck in a legal gray zone no engineering breakthrough can solve. One panel working is easy. 10,000 of them working together on the same building at the same second is a completely different fight. Not every window on a skyscraper sees the same sun. A pane facing south at noon pulls in full daylight, while the pane right beside it, sitting in another tower's shadow, produces almost nothing. That imbalance shifts minute by minute, all day, across every face of the building. Wire that the old way and one bad window becomes a heart attack for the whole system. Older solar arrays move as a single chain. If one panel chokes, it can drag the entire string down with it. An electrical cascade failure spreading from a single shaded corner to an entire floor. The fix works more like a neural network than a power grid. Every window gets its own small brain, reading and adjusting its own output independently, so no single pane can hold the rest hostage. All of those signals feed into one central system watching the whole facade in real time, routing power to whatever needs it most that second, whether that's the lobby lights, the elevator bank, or a server room upstairs. That software is the real brain in this story. Without it, 10,000 panes of smart glass are just an expensive wall. With it, the building stops being a stack of glass and starts behaving like a single living circuit. That's not a hypothetical piece of software either. Similar real-time balancing systems already run inside modern data centers and hospital backup grids, constantly shifting load between thousands of components without a person ever touching a switch. Solar glass just adds one more item to that same category of problem. China doesn't just dominate ordinary solar panels. Last year, more than 9 out of every 10 solar wafers manufactured on the planet came out of Chinese factories at a scale nowhere else on Earth can currently match. 2 decades ago, Chinese firms held a small sliver of the world's solar patents. Today, they hold roughly 2 out of every 3. And the companies behind that number now ship more solar modules every year than the rest of the planet combined. Beijing didn't nudge that industry forward with a few tax breaks. State banks and local governments flooded it with more than $50 billion over the past decade, a deliberate wave of cash large enough to sink almost every foreign competitor on price alone. That flood is now drowning its own shipbuilders. Chinese solar makers have been losing money for 10 straight quarters. More than 40 companies have shut down, and Beijing is now forcing its own industry to shrink on purpose just to stop the bleeding, an industry so productive it's suffocating itself. None of that dominance stops at cells and wafers. The same handful of Chinese industrial groups feeding those factories also run the float glass furnaces. Those cells eventually get built into. From raw sand to finished window, one country holds nearly every link in the chain. That concentration runs deeper than any single company. 1 out of every 7 solar panels made anywhere on Earth right now comes out of a single Chinese facility. Even that overcapacity has a silver lining for everyone else. All those excess factories are exactly why solar panels, and now solar glass, keep getting cheaper for buyers outside China too. The United States has one serious answer to that dominance, and it isn't a stimulus program. It's a small underdog company outside San Francisco called Ubiquitous Energy, built on a coating first engineered inside MIT. Their glass grabs ultraviolet and infrared light instead of visible light, leaving the window itself completely clear. They've already partnered with a major American window manufacturer to bring it into ordinary homes, and they're now racing to build their first full-scale factory before the technology gets buried by cheaper Chinese competition. Floor-to-ceiling versions of that glass, sized for real homes and offices, were expected to start shipping from a new U.S. production line as early as this year. Washington isn't just watching that race from the sidelines. In 2025, it hit solar imports funneled through Southeast Asia with tariffs over 3,000%, an economic blockade aimed at manufacturers accused of routing Chinese-made materials through third countries to dodge existing trade barriers. Europe is fighting the same war on a different front. Germany, Switzerland, and the Netherlands have started lining highways with solar noise barriers instead of ordinary concrete, treating every surface nobody thinks twice about as untapped grid capacity. The stakes underneath all of it are bigger than one product line. The market being fought over is projected to more than triple by the early 2030s, from roughly $20 billion today to nearly $100 billion. This isn't a fight over who sells more glass. It's a fight over who owns the blueprint for every office tower that hasn't broken ground yet. Both of the breakthroughs in this video, the light-bending coating from Nanjing and the tandem film from Mingyang, came out of the same country already responsible for the vast majority of the world's solar wafers. The question left for everyone else isn't whether transparent solar glass works. It's whether they can catch up before the next 20-year wall gets built somewhere else first. The era of glass that does nothing is over. This isn't a lab promise anymore. It's already bolted onto real buildings, generating real electricity right now. Ubiquitous Energy proved it on its own headquarters outside San Francisco, replacing a set of ordinary conference room windows with just over 100 square feet of transparent solar glass. That single wall now powers the lighting in the room behind it, using nothing but the daylight already hitting the glass anyway. Mingyang didn't stay quiet either. In the spring of 2025, the company carried its semi-transparent glass straight into Europe, setting up at Inner Solar, one of the largest solar trade shows on the planet, and put it on a stand surrounded by rivals from a dozen countries, daring every architect in the room to say the technology wasn't ready. Engineers who had once dismissed transparent solar as a marketing gimmick spent the show measuring samples themselves, checking the transmittance numbers against the company's own claims instead of taking the pitch at face value. Nobody in that room was asking whether a window could generate power anymore. They were arguing about whose version does it better, cheaper, and longer. None of this changes the math overnight. But every one of these installations chips away at the same argument that kept the idea shelved for 20 years. That a power-generating window would always cost too much and deliver too little to matter. Each one now sitting on a real wall is one more data point saying otherwise. Nothing about solar stays expensive for long, and the numbers prove it. The cost of a single watt of rooftop solar has collapsed by more than 99% since the 1970s, driven by nothing more dramatic than scale. That's the brutal law running underneath this entire industry. Produce more, and the price collapses. It has never once failed to hold. Analysts tracking transparent solar glass expect that same law to apply here too, just starting from a much higher point, with the current cost premium forecast to fall sharply within 5 to 7 years. North America and Europe are already losing the factory building side of that race. Asia accounts for well over half of the entire global market for this kind of glass, and nearly every new production line being announced is landing there, not in Europe or North America. The physics got solved in a handful of research papers. Who actually profits from it comes down to something far less glamorous: shipping logistics, tax credits, and who can pour concrete for a new factory the fastest. Energy economists have a name for that pattern: the learning curve. Solar costs have historically dropped by roughly a quarter every time global production doubles, no matter what the starting technology is. Transparent glass is just the newest material riding that same curve down. Utility-scale solar is now the cheapest source of new electricity in most of the world, according to multiple international energy agencies, a title it didn't hold even 10 years ago. None of the teams working on this glass think windows are the finish line. Windows were just the easiest place to start. Cars are the obvious next target. A handful of production vehicles, including hybrid models from Hyundai and Toyota, already carry solar roofs today, using ordinary black panels bolted onto the exterior. Swap that black panel for a transparent coating across the windshield and the side glass, and a car stops being something you charge. It becomes a machine that's always charging itself, topping up its own battery every single time it sits in daylight. Greenhouses are the stranger case, and the more useful one. A farmer running acres of glass has never been able to add solar cells there because the crops underneath need that exact light to grow. The fix is a coating tuned to slice off only the wavelengths plants don't use, close enough to a private lane for invisible light that engineers have started calling it photonic spectrum slicing, and it solves the problem without anyone choosing between electricity and food. Building windows are only a small slice of all the transparent surface sitting in daylight around the planet. Cars, greenhouses, and everything else made of glass are the much bigger prize waiting behind them. Not everyone in the solar industry thinks any of this matters yet, and their argument isn't really about the glass. It's about geometry, horizontal power versus vertical power. Rooftop solar already won the horizontal fight. It's cheap, proven, and scales by covering flat land nobody's fighting over: rooftops, parking lots, empty fields. A building can often hit the same energy target for a fraction of the cost, just by covering its roof with ordinary panels instead of its windows. But a 50-story tower doesn't have 50 stories of roof. It has one, and 50 stories of vertical glass wall standing mostly idle in the sun. That's the case for going vertical, and it comes with its own thermodynamic trap. Every photon a window grabs for electricity is a photon it isn't using to warm the room behind it in winter. In a cold climate, a building can end up spending more on heating than it earns back in electricity, depending on the season and the glass. None of that makes the physics in this video less real. It just means architecture is walking into a debate worth nearly $100 billion over whether power-generating glass becomes standard construction or stays a niche upgrade for glass-heavy towers in sunny cities. That vertical glass isn't a rare exception either. Full glass curtain walls have become the default look for new office towers built anywhere in the world over the last 2 decades, which means the surface this fight is happening on keeps getting bigger every year. This wouldn't be the first basic material that took decades to disappear into the background. Ordinary window glass went through its own version of this. Until the 1950s, flawless glass was ground by hand and treated almost like a luxury item. Then a British engineer named Alastair Pilkington figured out how to float molten glass on liquid tin, cooling it into a perfectly flat sheet without ever touching a polishing wheel. It took barely a decade for that process to conquer the entire industry, and today, nearly every window on Earth is still made using some version of it. Transparent solar glass is standing exactly where float glass stood back then. The lab work is finished. What's left is the slow march from a handful of factories to the global default. Buildings still burn more energy every year than every car, plane, and ship on the planet combined. That's exactly where this video started. 2 answers to that problem are already sitting on real buildings today. Neither one has won. So here's the question. If your building's windows could quietly become a power plant tomorrow, should every glass skyscraper on Earth be legally required to do it? Or should that decision stay with whoever owns the building? Tell me where you land in the comments.